Kegong Diao. I think some of you know Kegong. Kegong was postdocs about 10 years ago, right? Yeah, working David's fellowship on safe and sure. So worked here for about 2 years. About 3 years. Yeah, about 3 years. So now he's an associate professor at the Montfort University. So as you can see the titles here. So over to you, Kegong.
Thank you. Good morning, everyone. Thanks for your time for joining the seminar, particularly David. Really nice to meet you, and really glad that you come. So I have been working at Exciter, so basically on the Safe and Sure project, as introduced by Guantao. Thanks for the instruction. So basically, it's my great pleasure to come back because joining Exciter is probably the most important stage for my for the career development. So from here, I did learn the standard of good work. So for example, how to write good report, how to write good paper. And it takes me 2 years. So for writing a paper, meet a good standard. So thanks for David, Zia, Guantao, and all the others, who has very patiently guided me throughout the journey. So, and it took me 2 years, and after that, for writing a good paper, I can do it within a few days or few hours. So basically, I'm trying to pass this note. So, and also, the working experience here enabled me to find a permanent position at university. So I'm pretty sure that you have found, or you will find, the journey here is very fruitful in the future. So, yeah, talking about my research, I couldn't figure out a really good topic, so I just named as understanding with Pauling the complexity and data for urban water network analysis. So people in the house knows complexity, knows water network, so it's needless for me to really explain too much about the background. So, by the way, we are not that renowned as Exciter, but we do have a water software system there too, and we are trying to use whatever way possible to survive. So, apart from research, we also try to provide some, decision support tools to water utilities and trying to do some commercialization and consultancy. So that is basically our business. And in terms of background, I will make it simple. So I talk a little bit about the complexity, and then I will explain the complexity in urban water system and data, and then what we found from that. So that is the structure. So, well, needless for me to say, so you know this, right? So in terms of the complexity, so we have quite a few challenges. So we have complexity in our system, and we have bigger and bigger data thanks to the advance of technology. But then the question is how we use the data wisely and then to generate insights. Another issue is we are still lack of theory. So most of the work has been done based on empirical analysis. So, and for that reason, it's very hard to say, whether a method is efficient enough, is reliable enough. Not to mention there are some uncertainties. So I'm not going to tick the box of all of that. So I just focus on the first two parts, which is system and data. So for the complexity in water networks, the water network, right? So basically, it's to deliver water from a place to another using pipes. So there are topological complexity and behavioral complexity. So I want to use this as example. So XNet, so which is created by the Center for Water System here, which is a small part of a bigger system. But is actually, I think, complicated enough. Again, people in the house knows the system, so I just briefly talk about what is the mechanism. So we have reservoirs, and we use the pipe to deliver the water from the reservoirs to users and junctions, which is represented by the nose, by using the pipes. So as you can see, for such a system, to do some analysis, it's quite challenging. For example, if we want to find out the most critical pipes in the system, it's even hard to say from where we want to start. So certainly, we can do it pipe by pipe, but that causes issues. And there are some other methods like machine learning and GA method, whatever method. But we can use it. However, it's difficult to guarantee that the results are definitely reliable. Say, 100% sure that there is no missing of any critical links is hard to say. So then what we can do, one straightforward way is we can change the visual look of the system. So we don't need to change the structure, but we change the visual look. Say, how about we group some nodes and components together to view it as a cluster. So in such a way, basically, we see the system not from a whole, but from another scale. So if we change each of the cluster into a shape, so whatever you use, it can much easier, review some features of the system. So for example, from here, we can know that, we have the tanks delivering water. And in the other places, here we know there are lack of connections, and some other places there are some bit over redundant and can cause issues. So that is kind of straightforward application of this. And another thing is we can also explore the interaction among those clusters rather than see it component by component. So in this case, I plotted in such a way using the graph shows who is affecting what. So for example, you see on the top, we have cluster 5. So for any status change in this cluster, it will affect many of the others in the system. And for this one, it's probably the most vulnerable one because for whatever happened in the system, it may affect it. And for this one, it's just like more or less independent. For whatever had the system, it doesn't affect it at all. So that is the case. And this has been applied for some analysis, not only from me, but by quite a few researchers by using this kind of multi-scale clustering structure to facilitate analysis, for example, to identify critical pipes, to know where to upgrade, and also to support some other activities. So that is what is going on, to my best knowledge, in the field. So, but a follow-up question on this is, those are good things. Once we see the system in a cluster view, so it facilitates us a lot. And of course, we can also, decompose this cluster into subclusters so we can create the hierarchical multi-scale structure, something like that. So we can use it, but in itself, so our system do have this, so it seems a good thing, but in terms of the feature of the multi-scale structure itself, whether it is really good or there are still something we can do. So that is the research question I want to explore. And one direct question is whether the multi-scale structure do bring resilience, for example, multi-scale resilience. So that, and by the way, both of the research are kind of related to exciter. So this one is inspired from Feng Shui, and the other one was collaboration with the expert team. So our system do have multi-scale structure, but does this multi-scale structure bring our system resilience, particularly multi-scale resilience? So in this way, I just want to expand a little bit. So what is multi-scale resilience? So it's termed by scientists in urban planning, mines, and architecture. So quite, versatile. And you mentioned that multi-scale resilience is to coordinate different scales within a system to jointly cope and mitigate risk on any single scale. So it do provide a graph, which is very nice concept, but a bit abstract. Yeah. So here you see, so that is system, and it has different scales. So in this case, to me, we can view these as clusters, subclusters. So it is expected that the system should respond to any shocks come to the system together. Say all of them should interact and be able to cope with the shock. So then I think how to map this into our system and whether our system have this multi-scale resilience or not. And I evaluate a little bit, but before talking about that, I just further expand the concept of resilience. Actually, yeah. So I used the definition from David and his team. So the resilience, which is degree to the system to minimize the level of failure magnitude, duration, and maximize the time to failure impact. So I extend a little bit. So overall speaking is any shock comes, we want to know the magnitude of the impact, the duration of the impact, and the time for the impact to happen. So basically from this dimension. Yeah. Okay. So with this bear in mind, so if we come back to our system, I personally feel that our system is still not multi-scale resilient. So it's kind of mono-scale. And why? If we look at an urban drainage system, so traditionally how it works, we need it to deliver water. We need to deliver water to a certain place, and that's it. So we collect water from households and, put the water into a pipe, and then goes from upstream to downstream, and then reach the receiving body, and that's done. So regardless of how we see it, say, we see it component by component, that's the same. We see it cluster by cluster, it's the same. So it's from the upstream cluster, smaller one, to the downstream cluster. Once it's past the water delivered, and that's it. So for this reason, it do have issues. So for example, we designed the system in the way. So for the traditional design scenario, it works perfectly fine because anyway there won't be flooding and the design storm. So we deliver the water there and that's it. But in terms of resilience, because we deal with the extreme scenarios, so we will have, likely to have flooding. And then if we have this case, for example, here, we are about to have flooding. And if we want to do the same, say we want to enlarge the pipe to allow the water to go down straightforward, and yes, that is fine, but the water level here will increase and it causes flooding. And more water can go spike, and again, it causes flooding. So the way to simply to ask the system to deliver the water may not work if we consider the exceptional scenario. And for water supply system, it can be studied better because it allows the water to go back, for example, when we feed the tank and or we release water from the tank, it allows the water to go there and back, but it's normally local, not cover the whole rental system. And so following this kind of thinking, so I feel that the method to build the multi-scale resilience is rather than just allow the water to deliver from the source to the end, but also allow it to go back to the system. So in that case, we need bidirectional coordination, and we can, to create this, let's say, coordination, we can either increase the capacity at some places in the system, or we add actual pipes connections. So that is basically the idea. So I've used two very simple case studies, to expand the idea. So one is to allow actual capacity to allow bidirectional flow. So we can see this from a drainage system. So traditionally we have the system goes like that. We just deliver water to downstreams. And if we have flooding, so then we say we need bigger pipe here. So we want to let the water go. But the problem described previously will happen during extreme scenarios, right? It will cause flooding downstream. So the alternative solution is actually to enlarge the pipe at upstream. So it's like, say, the smaller scale, and to allow the water to come back and store there for a while. So in this case, we try to do the flooding attenuation. So basically that is idea. So-called we are using the surcharge and backwater effect. So again, for the resilience, we try to separate the normal scenario and the exception scenario. So under normal scenario, we're not allowed to have surcharge. But anyway, if during the extreme scenario, we will anyway have surcharge. So we try to use it. So basically what happened is we're trying to convert the traditional system into a resilient one by adding a new function, which is to allow buffer capacity. And the capacity allows the system to store the water at some point at some time to avoid any issues. So we need some new function in the system. But we need to carefully plan this, so we want to accommodate it at the right place and the right time. So basically, then I just think of what we can do with the system, and for the system, again, we can do some clustering on the pipes to see who are the smaller scale, who are the bigger scale, whatever, and then at each scale, in this case, normally referring to the different size of the pipes. So we work out what is the capacity, just enough to deliver water to downstreams. So based on the engineering design code. And in addition to that, if we want to further add any capacity, those capacity can act as a buffer capacity to allow water to go back, store somewhere. So I did a test on a small benchmark system. And what I found is, so that is a comparison based on some extreme scenarios. So for the design scenario, it's not necessary, it can be the same. And some extreme scenario, you can see that for the so-called multi-scale resilient design, we actually can use much smaller pipes at downstream. But instead, we try to use more space at upstream, so that to store the water. from where we normally can have more spaces. So there is analysis, and they found, well, theoretically, even we want to store the water at some places just for a few minutes or a couple of hours, it can significantly reduce the flood rate volume. So, yeah, so that is the idea, and compared with the traditional design to cope with the, extreme scenario, the cost saving is actually quite substantial. So, and another example, so which is about providing the actual connection to allow this bidirectional coordination. So it's a water supply system, and we have the water source here, and here we have the so-called, DMA distributing between the areas, that, but we can also see these as clusters. So we have system consisting of 5 clusters, and for each cluster, it configured with a pump to drive water to the region, and also a tank can intake water and also feed the system. So they are organized in such a way. So basically, we have the water, the reservoir here, and deliver the water to there, have some regulation, and also to the other clusters. So what happened is, well, it's actually brilliant design. It allows some, internal coordination within system. But the problem is, if any of the system has issues, so this cluster, the class 1 can support them, can still feed them. But the other way around, if we have issues here, they couldn't have, because it's only one direction. Right, so overall. So then I think what happened if we just add a connection to allow the bidirectional flow whenever needed. So in this case, if I add this and open it during some emergency, say, the man pump station is down, so that will allow this cluster to feed this one. And what happened is water supply in DMA1 can be planned for 2 hours. So personally, I assume this is a town. So here we have the town center, which means the main facilities are there, like a hospital or whatever. So basically, to plan the water supply during an event there is quite, substantial, quite essential. So, and not to mention, in this case, we just get one supporter. So if we have the support from all the other places, so the difference can be more significant. So that's why I think, well, it should be worthwhile. And overall, during the event period, the water shortage can be also reduced. So, yeah, that is the first part. The summary, basically, I explored, whether the multi-scale structure is multi-scale resilient. To my knowledge, is no. So we need to create the bidirectional interaction by either using actual capacity or connection, and try to verify it with a case study. It's a preliminary study. There's still a lot of work to do, but at the moment, conceptually, it seems work. I hope everything's okay so far. Yeah. So the second part is complexity in data. So we have the complexity in the structure, but we also, have issues in the data. So that's why I put it, as a separate case. So here I just, refer to the recent collaboration with Mohammed. So, so sector accepted for creating this opportunity. And again, people in the house knows data, so I just directly talk about the project. So it's a Horizon 2020 program, and it explores a cutting-edge idea, which is to heat recovery. I'm not an expert in heat recovery. So far, I still don't know exactly, what it's about. But I know is to try to regain some energy, some heat from the sewage, rather than waste it. And in this case, to simulate the hydrosulfide in the drainage system is quite critical because, as I understand it, the main source of the heat. So if we can simulate this and we times efficiency factor, whatever, then we can know, okay, whether the heat recovery is doable or not. So how to do this? We need to use big real-time data from sensors, which is brilliant to have the data. And the objective is we want to have real-time simulation and prediction of water quantity and quality in drainage network, particularly the hydrosulfide quantity and the concentration. So the vision seems to me that the water company, they are constantly collecting the real-time data, and we want to analyze the data and then to simulate and predict the hydrosulfide concentration, and based on that, we do some heat recovery work. And our DMU team is mainly responsible for the simulation part. So that is a case study site. So it's in Switzerland. There are 2 sites are monitored, and they use different sensors. So basically, we have some parameters like temperature, time, flow rate, velocity, or whatever. So which is brilliant. We get a huge amount of real-time data, but they are not directly usable. So because there are quite some challenges. So one thing is the synchronization of the large data set, because some data is recorded at 1 minute interval, some and the others at 5 minutes, and the rainfall data do not have a regular timestamp. So how to deal with that? And it also have high data uncertainty. So we have a lot of faulty data, we have outliers and invalid data, and they are hidden in the very large data size. I will expand this a little bit more later on. And there's no availability of hydraulic model. So they did have created a hydraulic model, and we confirmed with them, and eventually was not provided with hydraulic model. So, and apart from the difficulty in the methodology. So, actually at that time, I'm new to this as well, so I tried to learn the methodology, and I found that the Gaussian equations are actually quite complicated, and there are also discussion that whether it is applicable to the site or not, because, so maybe I didn't make it clear. So we measured the data from 2 factories, so, and we're not entirely sure exactly where they are in the system. So, and it also needs a lot of parameters. So that is challenging, and it's also in empirical, so we don't know which side of equation is the best. So then from the model-based solution, data-driven hybrid, so it's quite apparent to us that we have to use data-driven. So which means we solely rely on the sensor data, so which is the challenge. So, but we have the data, so we can use we try to use, the common way to solve it, but we have problem. So, for example, if we look at the data side, we found it's quite hard to understand by using the traditional method. Say, if we just use all the data as input, we put in the machine learning or whatever kind of statistics method, then we try to understand the result is very hard. It's very hard to us. So it's not directly implementable. So from here you see it shows the relation between the temperature and hydrosulfate concentration. So the temperature is more or less stable, following a pattern, slightly rising. But in terms of the hydrosulfate, at different sites, it shows different pattern, and there's no clear pattern. So by looking at it, it's quite hard to get the point. And also from some other side of data. So here is very easy to identify, but at some other places, for example, here, it's very hard to say whether they are abnormal or they are just some special cases. So that is the reason that we found it's quite challenging. And again, here it seems that they have two sides of data, for the same places, but using different sensors. It's quite hard to find out what is actually happening. So which one we need to use? So there are a lot of this kind of issues. It's luxury to have a lot of data, but it also brings a lot of challenges. So if we use the whole data side without any processing, it will be like that. So it's really difficult to know, recognize a pattern. So for example, here you see, although there are something looks good, but overall it's very hard to identify anything. So then I think, can I see the data segment by segment? So to try to find out anything. So, and if I choose one particular day, for example, and to plot this, I found it's actually quite apparent. So it's quite stable. So which is much easier to recognize. And also, if we check the flow rate, actually it follows a quite good exponential pattern. So then the idea is, okay, we see the data segment by segment, but we also try to identify the correlations between the segments. So for example, whether we can compare the weekend to weekend, Thursday, weekday, any weekday to weekday, and rainfall event to rainfall event, and festivals to festival. So in this case, is basically to consider the context. So not only what is happening in the system, but what is happening outside the system and how they affect the system. So, and by doing that, actually, we can find some clue. So the methodology is like that. It's not such a smart methodology, but we just try to make it workable at least. So first we do the data categorization. We have the system data. So it's all about the system, like the velocity, flow rate, water level. And we have contextual information, so which is so-called context aware. So we know the time, we want to know the weather, we want to know what is happening, the events, or whatever. And based on that, we do some data processing, and particularly we try to convert the contextual information into some values so that it can be easily analyzed. And it's just a normal procedure. Then we do the training, we do the validation, and here when we want to train the model, so we do this analysis. So we try to analyze all the parameters. So first, one by one. So for example, at each time we choose one parameter and then to see how it will affect the hydrosulfate concentration, because we want to simulate and predict the concentration of the hydrosulfate. So we then want to say how all these parameters will affect it. So we tried one by one, and then we combine all these system variables. So, 2 for each and 3 or until all. And then we include the contextual information, so which including the time and day or whatever. Based on that, then we try to find out the Bayes model. So throughout the way, using this kind of concept, we compare different machine learning methods. So basically, that I don't know whether I'm making it very clear or not. Just feel free to interfere if you need more information. So anyway, briefly, what has been done? So at stage 1, we group the data, system variables, contextual information. Then we try to do some data processing, and so we clean the data, and then we do some encoding to the data. Because normally, if we say the day and the time is actually text, right? So then we want to convert it to values. So for the day, we can use sine and cosine because so that is one day, and then another circle 2 pi is another day, and the time can be represented by sine or cosine with different angles. In that way, we convert the contextual information, some of them into values, so that we can see how these values will interact with side effects. And then it's just some normal process. So I didn't include this in the paper, but I include here just want to give you a more idea of the process. At the beginning, we do individual evaluation. So we see, for example, how temperature affects the hydrosulfate concentration, how the velocity will do it, and none of them shows very good results, which means using one parameter will not be enough. So then we try to increase the number of variables. So here we just consider the system variables, and there is actually big improvement of the results. But here we still have quite some issues. Then we like the machine learning to know the day and time and any other contextual information for the data analyzed. So we include those information into the test, and we found a quite substantial improvement in the results. So basically, we found the deep neural network provide the best result. We still have some problem, but at least for the project at the current stage, it's okay. It is submittable. So that is comparison between all the machine learning model we use. There are some models that didn't provide a very good result, but I hesitate to say it's a problem of the model. Probably it's because of lack of time. We couldn't do enough wise training on the model, so it doesn't provide a good result. But to some extent, it also reflects that using this deep neural network and some advanced machine learning method can save a lot of time to improve the results. So it's just another way to show how the results improves. So to summarize this part, the inclusion of the contextual information play a quite important role in improving the results. So basically, we have the R-square improved from 0.7 to 0.9 over 0.9. And interestingly, we also found that when we consider the different combination of variables, it actually the Bayes model is actually different, and it's not always that if we include everything into the model, then it provides Bayes results. It's not always like that. And at least in this study, the DNA model consistently outperformed the other models. So that's all from me. Thank you. Thank you very much.
Thank you, Kegong. It's great to see you have, followed the direction of safe and sure and done a lot of work in that direction. So, any questions from the room?
In your first presentation, on the end of case study 1, you had a lot of these nodes. Yeah, that's the one here.
This one.
Yeah. Can you please explain what have you done in when the search chart? What exactly? Because you mentioned the 5 sides or the space.
Yeah.
What are the differences?
Yeah. Sorry, because it's a bit compacted, so I probably didn't make everything so clear. So basically, the idea is we want to make a differentiation between the normal scenario, design scenario, and the extreme case. So, under the normal design scenario, so there will be no surcharge. So we can design the system following the traditional method using the design code. And based on that, then we iterate the extreme scenarios and to see how the system will respond. And because during these scenarios, it's very likely that the surcharge will happen because we cannot stop it happening in this case. So then the idea is how to use it. So how to let the surcharge do the work. Say to push the water back into the system and store it somewhere rather than release it in a very short period. So then where to store it? In that case, then we try to add the capacity beyond the design capacity. So then so that is the case here. So we can either put it downstream using the traditional method because it's just like say, oh, we don't want to have surcharge with that inlet it. Or we can say, anyway, it's not avoidable, so we allow it. Then we put it at upstream or somewhere else so that water can close back, store there.
Yeah, but these are the depth. These are the values from the depth. In 0.75, 0.825.
This one is the diameter. Sorry.
These are the diameter.
I didn't explain this. I think I didn't make it clear. So that is the diameter. Yeah.
So it's smaller diameter, but more filled.
Yeah, smaller diameter at the downstream.
Yeah.
And larger at upstream. This one doesn't show it's larger, but actually yes, the upstream should be larger. And,
okay.
Yeah.
Okay.
Okay, David?
Just a small point. Do bear in mind that in reality there are only fixed diameters for pipes. You can't get a pipe at every diameter.
Yeah.
Theoretically you can do it, but in
Yeah.
reality there's a fixed number.
I used the commercial value for this. So basically, it's like, well, it depends on the places, but I did check to get a table.
Yeah.
That is for Austria, so, and I use these values, which is, so if I increase it, the increment need to list to the nice,
The question I was going to ask you was, just stepping back to your definition, really, maybe just pull that up again on resilience, because you worked a bit on...
Yeah, so I just add up to this a little bit, because that is the extreme scenario. So if we want to cope with that extreme scenario, but if you use the traditional design and compare with this, so here that basically this upper will be bigger.
So I think, Kegong, was that depth in the pipe rather than the diameter?
Yeah, because the diameter increases, the depth is falling.
Most of them are small, yeah.
Yes, and even before that, you were talking about, so the diagram, maybe the top one, the previous one. Yeah, complexity. What do you mean by
behavioural complexity?
Yeah. So the behavior complexity is basically how the component they are interacting. So how the system behaves. So let's say because for this one, so it's topology component.
I've got that one, yeah, I understand that one.
So once we reduce it to this, then for that, it's basically we want to know, well, how those components they are interacting with
What
each
is the
other.
difference between that one and the previous slide? Why does that? Is that the same network we're talking about now?
It's the same network we're
Okay.
talking about.
But why? What do those lines mean?
Yeah, sorry. Again, I think I didn't make it perfectly clear. So that is still the topology
That
structure.
one?
Yeah.
Yeah,
So
I've got that one.
yeah. So and for that
Yeah.
is not the topology, and how I generate a graph is, for example, if there is any disturbance in the system, if it happened, then I measure, for example, the pressure change or whatever, and based on that, so if one place, so the state change at one place can affect another, so then there will be a arrow point to that place. So it's basically like the dependency, something like that, interaction. So for example, in that case, in this case, if there's, for example, pipe break in this region, and it will affect all of these clusters. So the arrows shows the impact.
So how do you calculate that?
I calculate that is basically using the matrix and some indicator.
Okay.
So for example, something happened here,
Yeah.
and then what had happened in the other places, and then based on that, I try to plot it as a graph. So it's called D-graph, and
Okay.
yeah.
So a bit like Robert Sitz and Fry's.
Work on networks, behavioural.
Kind of like that, yeah.
That would need a bit more explanation, I think.
Yeah. I think it's a bit,
Get my head around
bit
that.
jumpy and yeah. Thank you.
I think we'd like to get a question from online before we. I think we have a old safe and sure friend, Mariam. So Mariam, could you ask Kegong the question directly? Can you hear us? Yeah. Okay. No response. I think I'll do my best to read the questions. I have questions regarding multi-scale resilience in urban drainage systems. You mentioned that achieving multi-scale resilience requires buffers or extra capacities in different scales. My understanding is that these measures should not be limited to pipes and backwater system and manholes, but should also include overground options such as green infrastructure, retention areas or streets designed for temporary water storage. Could you clarify if the interpretation aligns well with what you explained about multi-scale resilience in urban drainage system?
I think yes, yeah, it's a very good question. So basically, the idea is really to create this bidirectional coordination. So it's regardless of what system we're analyzing. But it's just like that's what you said, is still quite abstract. So it is really, when we map into different systems, then it depends on what we need to do for it. So with the pipes, we can use such as, but is, for example, the white land or whatever.
Yeah.
So then it can be, actual channels, connections, or any other, facilities or natural solution. So it's just about, you know, how to use it. So, to my best knowledge. So I don't mean there are no other better solution. There may be some other ideas too. So far, what I found is
Okay.
this.
So could you also incorporate in other systems like a power system or transport system into the multi-scale resilience? Or it's possible?
Yeah, I think so. But first, I need to really understand the system.
Yeah.
So because in our case, I found, you know, we have monoscales rather than multi-scale, at least at the current stage in most cases. But for the power system, then we again need to analyze the system to see whether, you know, it has multi-scale already or not. If yes, then how? If no, then we use this. If yes, then how to improve that? So it really depends on the feature of the system. What is the current stage?
Okay, yeah, that's great. Yeah, Pete?
How much the heat recovery process? How much is that affected by the depth of water in a, let's call it a circular pipe? So, do you want bigger surface area as possible, or as little surface area as possible?
Very honest speaking, I don't know.
I was just going to go to the fact we're trying to keep less product in the pipes as possible.
Yeah. So because to me it's something really, really new too, and I haven't really got time to look into, you know, that much of detail. So yeah, it's more about task oriented. So now I need to do simulation, or I need to submit something useful for team. So I just try to analyze this database. But by some, you know, analysis later, I think we can fund it out. We can fund out. So basically, it's about in which way it can have to retain the heat, and also facilitate the harvest of it. So I think we will be able to fund this out.
Hi, Kegong. It's lovely to have you here. Thank you for covering maybe 3 different spaces. I'm going to take you back to the stormwater pipes that Mohammed was looking at. And my question is, if you could get a swim model or a hydraulic model from Severn Trent Water for 100 of their networks, would you be able to use a version of your method to either suggest or test which locations maybe we could add a throttle pipe within their networks? So, and thus say, reducing this pipe size on this street provides you this benefit in this catchment? Because I feel like there's a Hydro International PhD, is it Mr. Newton, Dr. Newton?
Indeed.
He looked at installing flow controls in networks. And to some extent what you're saying here is to constrain the network in certain locations. Anyway, I'm wondering if there's something to be said in terms of a follow-on study in that space.
That is very interesting. So if I can be involved, then I will be really excited. Because, and for this, another thing is really trying to tackle the challenge in, you know, more efficiently used underground space.
Mm-hmm.
So in this case, even for the large cities, we see the potential of not, you know, substantially enlarged pipe, but we can just, you know, maximum utilize of the capacity.
Yeah.
And also, what you said actually recall me of, you know, what happened in the Safe and Serve project in the steering group meeting, you know, organized by every Brazilian team. So there is industrial partner, and they say they are using, like you said, valve, and then to really, you know, isolate some pipe, load water, and basically share a similar idea.
Mm-hmm.
And in this case, I want to make it even more kind of automated rather than you know, manipulate the valve, so it can also, you know, kind
So it operates passively in a better
better
condition.
Way. So we can combine this together. So some places we use valve, some places we use.
Back on this, don't quite understand why most of the numbers in the multi-scale resilient example are smaller than the traditional, unless the traditional was always far too big in the first place, and that it could have still been smaller yet and deal with traditional use, because nearly every single number in your multi-scale set is smaller than the traditional.
Yeah. So it honestly takes me time to recall because it has been quite a while. So I also wondering why. But if I remember correctly, so for this one, it's not for the common design scenario. So it's for an extreme storm beyond the design scenario. And if we want to use the traditional method to accommodate all the flooding result, and result such as, and we need pipe size at those levels. But if we use this kind of allow such a solution, so which is different from the design, then those pipe size will be enough. So, but if we do the design under the same kind of design scenario, because anyway they will be no surcharge, and then the two designs can be the same, or this one can have larger pipes upstream to reduce flooding and a certain range of storm scenario out of the design scenario. So basically, I hope that is the case.
Sorry, we have more questions online. Unfortunately, I think we run out of time. The people are waiting outside. So I think probably Kegong, could you get back? To the question after the seminar? So probably can have. Yeah. So thank you all for coming to this seminar. So I think I'm sure you join me in thanking Kegong.